Let's study about integration. And all of us are familiar with a lot many graphs in physics, like velocity graph, pressure volume graph, a lot many. So let's consider a very simple example. This is a graph. Here we plot velocity, and here we plot time t, time. And suppose the graph is horizontal. The graph is a horizontal line, and with the velocity 5 meter per second, and the time of travel is say 10 seconds. Now the graph is a straight line, segment, and this portion is a rectangle. Geometrically, I am finding the area by using the formula length into breadth case. You know, the length is taken to be 10 seconds and the width is 5 meter per second. This is 50 meter. So geometrically, I found out the area under the line. Dimensionally, it is displacement. So we conclude that the velocity time graph gives displacement. Velocity time graph gives displacement, or simply the area VT graph gives displacement. Now take another graph. This is the pressure volume PV diagram. We call it as a PV diagram or indicator diagram. Suppose this is a graph, and this volume is V1 and this volume is V2. Again, I find out the total area. This total area is found to be work done by the gas in changing the volume from V1 to V2. That's the meaning of area under the curve. Now take another example. Suppose when a cricket ball hits a bat, the ball will exert a force. It's called impulsive force. That force will exist for a short interval of time. And the variation of the force, impulsive force, with the time gives this graph, this type of graph. So that it varies and reaches maximum, then decreases. Again, I can find out the area under the graph, area under the curve. Here I can show that this area is nothing but impulse, force into time. Area under the area under force, impulse, force, time graph gives impulse. Now say this is force, again displacement, and if you find the area of this force displacement, again we get this area as a work done. So in lot many situations we encounter or meet this type of graphs, and we find the area under the curve. And in the simple cases, it's easy to find the area. If it is a rectangle, you know the formula. For a trapezium, we know the formula. Right angle triangle. But what about this situation? Suppose I draw a graph like this. Suppose this graph is y is equal to some k x raised to n. I want to find the area under the curve from this is x is equal to a and this is x is equal to b. So we want to find out the total area under the curve. What I do is I divide the curve into larger number of small segments. This is one segment I picked up. This is one small segment of width dx and the height of which is y. So what is the area of this strip? Area of the strip is y into dx. Height is y, width is dx, y dx. So to find the total area, what I do is I divide this whole portion, the graph under the portion, into larger number of small segments. So I find the sum of the whole segments, area of all segments. So I write the symbol summa, add. So cut and add, chop and add. The whole curve is divided into large number of strips. Take area of one strip and then add all the areas together. So we write this as the area under the curve from A to B. This is the case. And why we know it is k x raised to n into dx from A to B. There's a simple formula for calculating this quantity. As constant k comes out, then x raised to n dx is x raised to n plus 1 by n plus 1 from A to B. First I put a upper limit for x. So it's a b raised to n plus 1 by n plus 1 minus n plus 1 minus put x as a. So a raised to n plus 1 by n plus 1. This is a formula we have. Now let's do a simple example. Suppose I take a y is equal to x square case. Y is equal to x square. I want to find the area from 0 to 3. 0 to 3. 0 to 3. This x is equal to 3. So I need the area under the curve from this position. Apply the same rule. So area is equal to integral from 0 to 3. One strip is of width dx, height is y. So y dx, the area of the strip. Total is this one. And I replace this y by x square into dx from 0 to 3. And this x square dx is x cube by 3 from 0 to 3. Then I put a upper limit first. 3 cube by 3 minus 0 cube by 3 is equal to 9. This is exact the formula and exact answer. Now let me solve this problem, finding the area graphically. Draw a graph here. Simple graph is drawn. So 2, 4, 6, 8, and here comes 10. So again, so 1, 2, 3, 4. The graph is y is equal to x square. I want to plot y is equal to x square. Y is equal to x square. So when x is equal to 0, the point is 0, 0, 1, 1, and 2, 4, 2, 4, and 3 comes 9, 3, 9. This is y is equal to x square. Y is equal to x square graph. Now to find out the area under the graph, I count the total number of complete squares. 1, 2, 3, 4, 5. So area equals 5 plus, and some squares incomplete, I partially filled squares will be taken, and half of which will give you the right answer. So half into 1, 2, 3, 4, 5, 6, 7, 8. So it is 5 plus 4 is 9. This is the approximate way of doing the integration. This is the exact formula, and here in this case I plotted the graph y is equal to x square and then found out the number of squares, or in other words, I find out the area under the parabola from 0 to 3, which is around 9. But if you in most of the time, we get the approximate answer. In this, fortunately, we got a coincident numbers. Now we see some applications of this integration technique. Here we have a graph. This is a velocity time graph. This is a velocity time graph. I take again, here we take a small segment. Small segment is taken. Height of which is v, and width is dt. So area of this portion is a vdt. Vdt is the area from 0 to the final time is t, 0 to t. You know that area of velocity time displacement is, and this v is equal to u plus at. So I plus v u plus at all into dt from 0 to t. I write this as u t raised to 0 dt integral from 0 to t plus at dt from 0 to t. This is u into t raised to 0, t raised to 1 by 1 from 0 to t plus a into t into dt, t square by 2 from 0 to t. And the answer is, simplifying the upper limit and lower limit, okay, you get ut plus half at square. Now take another example. Suppose we stretch a spring. In that case, work done in stretching a spring can be obtained from this formula, F is equal to kx. Now, F is equal to kx is a formula for force in stretching a spring. And suppose we stretch the spring to a small distance. I take this force as F, and small stretching is dx. So total work done is equal to the total area under the graph, which is F dx from 0 to x. F is kx dx from 0 to x. K constant x dx integral x square by 2 from 0 to x. Substitute we get half k x square. This is the work done. Here the force is variable, and we found out the total area under the graph from 0 to x. This is the work done, and this work done is stored in the spring as potential energy. Now think of charging a capacitor. Suppose we take a capacitor and we give battery to charge this capacitor. At a particular moment, the charge on the capacitor is Q and the potential difference is V. And the potential difference gives the work done in transferring unit charge. So work done in adding a new charge dq is V dq. So total work done is integral V dq from 0 to final charge Q. And we know the equation for capacitance. Q is equal to ZV. Q is equal to ZV. So we replace V by Q by Z, Q by C dq from 0 to final Q. 1 by C constant Q dq integral Q square by 2 from 0 to final charge Q. We get Q square by 2C. Thus we found out the expression for work done in this case. Similarly, we can find out work done in any case, or in general, if the y coordinate and the x coordinate are related by a function, we will be able to calculate the work done. Here we cannot simply multiply force by total stretching, because force varies. When you stretch a spring, force varies from point to point. That's called variable force situation. In such situations, we use this process called integration.